we are going to go over an extremely simplified version of what happens in an action potential. And I want you to just sit back and listen, and we'll go over this again, and you can take notes then. I want you to understand the concepts before you start trying to take notes. So to keep my own life simple, I'm not drawing because I have no artistic skill. And instead of writing out all of the charges on these ions, because all ions have charges, if you hear the term ion, it means charged particle. I'm just keeping things simple. I'm just going to write Na for sodium and potassium, K for potassium. So in a typical cell, you're going to have slightly more potassium inside the cell than outside the cell, and slightly more sodium outside the cell. There will be a little bit of sodium in here, and a little bit of potassium outside. But the concentration of sodium will be greater outside of the cell than inside the cell. That makes sense so far. So we're talking about your standard neuron at rest. Because of the fact that you have a different concentration of ions on either side of the cell membrane, you have a very slight difference in charges, which is going to be negative 70 millivolts. So it's tiny, you're talking millivolts. Tiny, tiny, tiny difference in charges. And that, when the concentration of ions is like this, that is what's going to give the cell what is known as a resting membrane potential. Nothing's happening, the cell's at rest. There's a slight difference in charge, negative 70 millivolts on either side of the cell membrane, which gives that resting membrane potential. They're not absolutely sure, physiologists aren't sure why this happens, but for some reason it does. The cell starts to become stimulated, and there are going to be gates in the cell membrane, which are noted as sodium gates, and sodium gates will open, which means that sodium will start to rush into the cell. Right after that happens, potassium gates are going to open, and potassium is going to rush out of the cell. You have sodium rushing in, and right after that happens, potassium is rushing out. So you end up with a slight concentration gradient difference, which is the reverse of what it should be. And there'll be potassium still inside the cell, and some outside the cell also. But there's a change in concentration gradients of those particular two ions, the specific two ions. Make sense? Doesn't like that. The cell doesn't like that. So you're going to have a pump, which is known as the sodium-potassium pump, that is going to come into play and start pulling sodium out and potassium back in. So the sodium gets pulled out, the potassium gets pulled back in, and then you reestablish the appropriate concentration gradients. So you have more potassium inside the cell, than outside the cell, and reestablishes the sodium concentration, so you have more sodium outside the cell again than inside the cell. So far, so good. This, when the cell is at rest, you have that resting membrane potential. When you have that shift of concentration of ions, the cell is depolarized. And then when the sodium-potassium pump reestablishes the appropriate concentration gradient, the cell becomes repolarized. right after this happens, right after the cell is repolarized, there's this minute, teensy little nanosecond of a break, which is known as the refractory period, where the cell cannot be stimulated again. The neuron cannot be re-stimulated during the refractory period. So what actually happens, I drew this as if it's all happening within the cell at the same time. What actually happens is information comes in either on the dendrite, some sort of threshold is met either on a dendrite or the cell body, and the changes in ion concentration is going to happen in tiny little portions of the cell membrane. So it actually travels like this and then down, out, and along the axon. It doesn't happen all throughout the entire neuron. It's going to happen in tiny little increments of the neural axon. And that's what you need to know. And there's way more information in the PowerPoint than in the text than what you need to know. You need to understand this. In the normal resting cell, slightly greater concentration of sodium ions outside the cell than inside the cell. Slightly greater concentration of potassium ions inside the cell than outside the cell. So that gives the resting membrane potential of -70 millivolts. Since your threshold is met, the cell becomes stimulated, sodium gates start to open, so sodium will start to flood the cell. Right after that happens, potassium gates will open, and potassium will start to flee out of the cell until you end up with the opposite concentrations that you should have. So there'll be slightly more sodium inside the cell and slightly more potassium outside the cell. And then the sodium-potassium pump will reestablish the appropriate concentration gradients. It's way more complex than that, but that's what you need to understand. I want to talk about, erase some of this, and sit back, keep listening, I have to take notes. I'm going to erase some of this so I can be close to the camera because I need to talk about what happens along an axon. Because if you remember, here's our neuron, here's some dendrites. And then you have an axon. And if you remember, some of those axons are going to have myelin. Each of these sides is a myelin sheath. The axon is going to run deep to that myelin sheath. If you know what a Swiss roll looks like, with that wrapping of the cake around and around and around and around, the axon is in the middle and the myelin is basically around, surrounding that axon like a Swiss roll. So what actually happens when you hit that myelin sheath? So back in the day when they were trying to figure that out, they thought that the action potential hit the myelin sheath and then leapt to the node of Ranvier, ran through the node of Ranvier, then leapt to the next one, and then the next one, and then the next one. And the word for that, the term for this movement of an action potential along the axon is known as saltatory conduction. This comes from the French pour tout. So it comes from the French verb pour tout, because I thought it leapt from node to node to node. What actually happens is this. The myelin acts like an insulator. So the sodium and potassium gates don't open. And it is actually, the action potential happens along the area that doesn't hit myelin. And then you're going to hit a local electrical current that is carrying that information down along underneath the myelin sheath. You have an action potential in the node of Ranvier. Over here, they can see what I'm doing. You have an action potential in the node of Ranvier, then you're going to have another electrical current carrying the information, thank you, along underneath the myelin sheath until you get to the next node of Ranvier where you'll have the action potential occur. And then you'll have electrical current carrying the information under the myelin sheath until the next node of RNA where it has another action potential, et cetera, et cetera, et cetera, and so on and so forth. So what's actually happening is there's an electrical current that's carrying the information underneath the myelin sheath. The gates are not opening. So an easy way to think of it, and this is an analogy, an easy way to think of it is this, that basically that action potential builds up enough momentum to send local electrical current underneath the myelin sheath until the next area where it kind of builds up more momentum in the node of Ranvier, where the action potential will occur, until you hit the next myelin sheath to build up enough steam to local electrical current to carry it under that myelin sheath, and so on and so on and so on. This is why those myelin sheaths are so important. People love to tell me, students love to tell me, oh, the myelin sheaths are for insulation and protection, and they are. The major reason that you need to be interested and concerned and excited about these myelin sheaths is because of the fact that they can speed the conduction of an action potential. Look, they can speed the rate of an action potential up to 250 miles an hour. That, yes, it's one of the many reasons that's important in this. Yeah. So when you hear these terms, you're going to hear the term, everyone's heard white matter versus gray matter. When you hear white matter, you're talking about myelinated axons. And there's going to be a bridge between the two hemispheres, which is known as the corpus callosum. Let me see if I can find that. Slide model. The corpus callosum is a bridge of white matter in between the two hemispheres. Let me get to the camera. Here it is. This guy right here is the corpus callosum. It is, if you're asked to define or tell me what the function of the corpus callosum is when we get to the brain, it is a bridge of white matter between the two hemispheres, brain hemisphere, left hemisphere. And that is why information can travel back and forth in your brain so quickly. And up from some sort of sensory input, up a sensory neuron, get processed in the brain, and then you have a motor output. That's why you can do it so quickly, because that, a lot of that information is traveling at 250 miles an hour. Which is like astonishing, isn't it? There are neurons or axons that are unmyelinated. And sort of classically, the neurons that are associated with carrying information or chronic pain are unmyelinated. So think about that for a second. And why might the fact that they are unmyelinated be important? Or why might they be unmyelinated? So the question is, would you want chronic pain to be carried on myelinated axons? No, because it speeds up. Yes, correct. You should say correct. You don't, because you would be overwhelmed with the sensation of pain. It would be overwhelming and you wouldn't be able to do anything else. So when we talk about patients who have some sort of chronic pain syndrome or known chronic pain, that information would be carried on unmyelinated axons. So the patient is not totally overwhelmed by the sensations and perceptions of pain. Probably, yeah. If you're putting your hand towards a hot stove, you want that information to be carried on myelinated axons because you don't put your hand on that hot stove. You don't want to touch something. And since we're talking about that, let's do a segue into a spinal reflex arc. Because we're going to talk about all of the components really quickly of the nervous system. And I'm going to stop this recording. Please have recorded, and I'm going to start up the second one. So I have two.